Well, we've certainly got a very intense topic tonight. This is a real powerhouse topic that is certainly one of the more complex ones of the year. But we're going to take it step by step, and I'm super confident that by the end of this video, we're gonna be in it. We're going to be in it for sure. So we're talking about annual rates, okay? And what we're going to really get into is the frequency upon which a rate occurs at. So you say something's increasing at a rate of 24%. Is that 24% every year, or is that 24% every 2 years, or every 5 years, or exactly how frequently does that percent roll over? So this formula that we've got, we're basically just adding and continuing to develop the general form of an exponential function that we've been working with. So you'll notice that basically everything is still the same, except for up there in that exponent, the t is now divided by n. And so that's the new aspect that we're getting into. So again, we'll define a as our initial amount, just like we always have. That's our initial amount. And r is the rate that the function is growing or decaying. Okay. And another word for rate is, percent. We think of like percent change, like last night's topic. T is going to be our time. Now, typically that's measured in years, but we got to be very, very careful. It could be measured in months or days or hours, and we just have to be really on top of our game with paying attention to what the units are for that particular problem. And then N is going to be our frequency. In other words, how often does that percent occur? And so when we think about the fundamentals of what it's going to take to be really, really good today, it comes down to being really comfortable with what's called the power property of exponents. Okay. And this is usually the third one that you learn. And it looks a little like this. You'd say, okay, I've got x and maybe it's raised to the a power, and I want to now take that expression and raise it to the b power. So in essence, you just multiply the two powers and you get x to the a times b. So that's what the power property says. If you have one power raised to a second power, you just multiply the two powers together. So in this particular case, I've got x squared and I want to raise it to the sixth power. Of course, what we could do is we could repeat that x squared 6 times. That's one option. And that's a good option as you're trying to make sense of how this really works. And now you say, okay, let's add, the 2, the 2, the 2, the 2, the 2, the 2, and those add up to x to the 12th. But of course, the shortcut is we don't have to add those up. We could just multiply the 2 and the 6, and you'll still get that 12. So that's why we're saying multiply. So in our next example, we'll multiply the 3 and the x, and you get x raised to the 3x power. On this next one, we're going to multiply the 1/3 and the t, and you could say 1/3 times t, or sometimes we'll say x to the t over 3 would also be equivalent. And then the fourth one here, we could say, okay, let's multiply the 1/5 and the t, so x to the 1/5 times t, which is going to be x to the t over 5. So now what we want to do is, once you're comfortable kind of going in that direction, we're going to reverse engineer the process and kind of decompose that exponent or break it into a smaller piece. So in this particular case, we could say x to the 5a is really x to the 5th raised to the a power. Okay, so we're kind of just going backwards. We're reverse engineering it. This next one is going to be x to the 1/2 raised to the t, because t divided by 2 is equivalent to 1/2 times t. Okay, so instead of saying t divided by 2, we could just say 1/2 times t, and then kind of pull them apart, separate them, and you've got x to the 1/2 in parentheses raised to the t. So a similar idea on this next one. When I see t divided by 10, I'm really picturing 1/10 times t. So if I've got x raised to that, I'm going to separate it, and I'm going to go x to the 1/10, and that quantity is being raised to the t power. And last but not least, we could do x to the 1/8, and that's raised to the t power. And just a way of kind of double checking my work and confirming whether what we're doing is legit or not, we could say, okay, what if I multiply this guy and this guy? Yep, equals that. Or what if I multiply this power and this power? Yep, equals that. And we could just double check our work that way. So that's really the underlying key fundamental to being good at what we're going to try to accomplish today. The following function models the population of Grizzly Town. And so we want to work on what we call our interpretation. So the initial population is 1,200. And is growing at a rate of 24% every 4 years. Okay, now I'll kind of backtrack a little bit and talk about how I got all those values. So in this case, your A is your 1,200. That's your initial value. The 1.24, that's equivalent to 1 plus 0.24. So, and then move that decimal twice, so you're getting that 24%. And then you'll notice the exponent here, t divided by 4. So, like we said in our early definition, t divided by n represents the frequency. So in this case, we could say our n value is a 4, which is the frequency upon which that rate will kick in. So it's going to be 24% every 4 years. Now, what's an equivalent function? Because naturally you're like, okay, so it increases 24% every 4 years, but how much is it increasing on one individual year, on one single year? And unfortunately, it's not as simple as just taking the 24% and dividing it by 4 years. If we've learned anything this past week, it's that these percentages, they behave in some interesting ways for sure. So what I'm going to do is I'm going to decompose that exponent. And I'm going to rewrite g of t as 1,200. And then it's going to be 1.24 raised to the 1/4 power. And that's in parentheses raised to the t. So we're kind of instead of t divided by 4, we're kind of visualizing it. And I'm going to make a note here. T divided by 4 is equivalent to 1/4 multiplied by t. And then we're just separating those two things. So the 1/4's on the inside, t's on the outside. Now all we got to do is let's just enter this into our calculator. And as a rule of thumb, we'll go 4 decimal places on all of these today. So you can kind of make that note that we're planning on going 4 decimal places on all of these. Okay, let's see if this makes sense. I'm getting 1.0553 once I round it. So g of t is going to be 1,200 and 1.0553 to the t power. So now we can make a new interpretation based off of the way it's written. Of course, the initial population is still 1,200. That's never going to change. But the interpretation now is the population is growing at a rate of 5.53% each year. Okay. Now, how did I know it was each year? Well, when you look at your exponent here, it's essentially just t divided by 1. So the frequency is 1. So it's going to be each year. So, and these are equivalent statements, 24% every 4 years or 5.53% each individual year. All right. So the following function models the number of Josh Allen jerseys sold after each game the Bills have played so far this year, where T represents not years. Notice this, T's going to represent the number of games played since the beginning of the season. All right. So what's our initial interpretation the way it's written? Okay. The initial number of jerseys sold, we'll say initial number of jerseys sold was 420 and is increasing, or we could have said growing. That's totally, acceptable, of course, is increasing at a rate of 84% every 6 games. Okay. So we're increasing at a rate of 84% every 6 games. Naturally, the question is going to become, well, at what rate is it growing or increasing after each single game, each individual game? So let's see if we can rewrite the original function. Now, the note that I'm making to myself is that exponent, t divided by 6, is really equivalent to 1/6 times t. And then we're going to reverse engineer that power rule. So g of t is going to be 420 times 1.84 raised to the 1/6 power, in parentheses, raised to the t. So then all I've got to worry about now is plugging the 1.84 to the 1/6 into my calculator, and we'll try to round that to 4 decimal places once again. 1.84 raised to the 1 divided by 6 power. All right. So we could rewrite the equivalent function as g of t equals 420. I've got 1.10, and I've got 697, which is going to cause me to round to a 70. All right. So now the new interpretation here is that of course, like we said, the initial value is still 420, and the number of jerseys sold is increasing at a rate of 10.70% after each game. Yeah, baby. The more they win, the more jerseys they sell. Let's go, Buffalo. We're going straight to the Super Bowl. You know it. You know it. Super Bowl, here we come. All right. The following function here models the amount owed on Ray Ray's college loans. Okay. And what we'll do is we'll define T as being in years. I should have stated that there. I noticed I omitted that. So T is going to be years since Ray graduated. And that, once he graduated, he had to start working at paying back that college loan. And so this function is going to tell us how, what the balance remaining on that loan is going to be, after T years. So the interpretation right now is the initial amount owed was $84,000 and is decreasing at a rate of 8%. Whoops, there's my 8. At a rate of 8% every 2 years. Now, if we need a timeout here, we can call timeout and say, well, how did you get that 8%, Mr. Hill? Well, the base, in this case, anytime it's decaying or decreasing, the base is 1 minus r, and that's equal to that 0.92. So what we could say is negative r is equal to negative 0.08 if I just subtract 1 from both sides of the equation and then divide both sides by a negative 1. And then, of course, we'll take that decimal and move it twice to convert it to a percentage. Okay, so naturally the question that's going to evolve out of this is, well, at what rate is the amount owed decreasing each single year? So let's see if we can devise an equivalent function. And feel free to go ahead and give this a shot if you're starting to feel a little more confident here. 84,000, and then we'll go 0.92 raised to the 1/2 raised to the t. We'll evaluate 0.92 to the 1/2. 0.92 raised to the 1/2. Ooh, okay, 9592. So an equivalent function would be 84,000. 0.9592 raised to the t. All right. So, before I make my new interpretation, I always think these decay ones are always harder, right? So I'm going to do a little scrap work here. If we know that our base is a 0.9592, then that means 9592 equals 1 minus R. R equals 1 minus 0.9592, 0.0408. Okay. So that's my rate of decrease. So my new interpretation is going to look like this. Okay. The amount owed is decreasing at a rate of at a rate of 4.08% each year. And I guess that kind of ties in with the title. Our title was like annual rates. So, what's happening? What is our percent change each year? And so taking what we know about every 2 years or every 5 years or every 8 years and kind of working backwards to figure out what that percent change is going to be each year.